All right. I see so far only 25 people. I think I have many more, which means it's time for a class photograph. That's a way to take attendance. So turn on the cameras, say cheese, smile. Here we go. Okay, guys, more mercy for those that turn camera on, you know. All right, I suppose you think you don't need my mercy. Fine with me. But I was inspired by just listening to the biblical account of the destruction of Sodom and Gomorrah. Just this moment. And comparing it to the English translation. Good? So, you are aware when the exam is due, correct? Because I'm not. So let's go with the lecture. So guys, today I hope you find this topic extremely exciting. Expectation of a function of a random variable. And it's a very simple idea. It just means that, guys, what is a random variable? It's just, simply said, it's a relabeling of the elements of the sample space. You understand? So you can just take the individual elements of the sample space and some of them can be assigned the same label, right? You are free to label them as you want. You can think of that mathematically also as assigning the sample space to a new modified sample space. It's called induced sample space. And all that means is that the variable x is an onto function, right? So in other words, you just to decide what labels do you want to have, and each label must receive an element underneath it. Good? As simple as that. Now, when you say function of a random variable, that just means that you want to relabel. It sometimes is convenient to carry the labeling through an intermediary process. It's a label of a label. Understand? So one way to think of that is, here is some illustration, guys. So we have a sample space with equally likely outcomes. There are 5 outcomes, outcome 1, 2, 3, 4, and 5. They were each assigned the same weight, the same probability. Good. And then the random variable x will map the first 3 to -1, the 4th outcome to 0, and the 5th outcome to 1. You can think of those as payoffs. Now you see I drew it as S star, and I drew it as a separate sample space. You can equally well just relabel 1 as -1, 2 as -1, and 3 as -1, and keep their probabilities. Or you just say, well, they are all gathered into one outcome, which I call outcome -1, and its probability is the sum total of the individual probabilities of the outcomes that made it. So far, very clear, yes? And then I can carry out this function, guys, the function g of x equal to x squared, which means that my labeling will be squaring the outputs of x. And you can see that 1 and -1 are mapped to 1 and 0 is mapped to 0. So that's the end result. Yet what truly happened here? What truly happened is that outcome 4 was just labeled as 0. Whereas all the other outcomes were labeled as 1 at the end of the process. You understand? So really, it temporarily, there was a separation of some outcomes going to -1 and some outcomes going to 1. But at the end, all of them were mapped to 1. Right? So g of x equal to x squared means just another reassignment, another labeling, nothing more. Understood? So x squared is another random variable. Right, so then of course there is the issue of calculating the expected value. You all remember what expected value is, and there is no need for me to repeat the explanation, yes? Expected value, you understand how the formula comes about. You just multiply the numbers that are produced from the random variable by the probabilities, by the likelihood of those numbers appearing. Good. So what would be the expected value of the random variable x squared, of the random variable here, x squared? It will by definition be simply 1 multiplied by the probability of getting 1 and 0 multiplied by the probability of getting 0, right? So the expected value of x squared by definition it's this. And you all understand how the definition was made. Yes, guys? Notice that there is a big difference between the expected value of x squared and the expected value squared, right? The expected value of x is the values of x multiplied by the probability. So it's -1 times probability of -1, 0 times its probability, and 1 times its probability, and then you square it. And the result is 0.16, which is very different from 0.8, right? The relationship between them is not so, you know, it's definitely not equality. Good? You understand what this means, guys? This just means we carried a bunch of labelings, and then we average the labelings. How many times do we see them occur in experiments? What is this? It's just the square of the average of another labeling. So there is no reason why the two should be equal. Good? Notice, however, guys, that we could have calculated the expected value of x squared differently. You agree? We did not have to group together the probabilities. We could have just taken the x and squared the value. So it's -1 squared times the probability of -1 squared plus 0 squared times that probability plus 1 squared times that probability. Good? So both results produce exactly the same thing. Now, what do I mean by that, guys? Right? So here is a general proposition, and it's written technically, but what it is saying is tremendously simple. Okay? Tremendously simple what this is saying. I already explained, hopefully. It's just a matter of relabeling. Let me try to draw you a picture and hope that this picture would make you understand the two ways by which we can calculate the expected value of a function of a random variable. Good. So this is a sort of drawing here, right? So here is the sample space, and let's suppose we have outcome 1, 2, all the way to outcome n. When and they have the corresponding probability. So probability is p1, this probability is p2, all the way to probability pn. Yes? Now, when I apply a random variable, I just group a bunch of them together. So I just relabel. So if I apply the random variable x, this becomes x of 1. This becomes what is the relabeling of 2, all the way to the relabeling of n. You understand? That's what really all that happened. We can think that we are still stuck in the same sample space. Ruadra, please go ahead.
So with this random variable, I have a question. So you're saying it's a relabeling, but would the original like function count as a random variable? Like you're labeling 1 to p of 1, 2 to p of 2.
No. It's not a relabeling. This is the probability. You see. So on the left, it's just the probability, the likelihood. If I run an experiment, let's say in this experiment, I have n outcomes, outcome 1, 2, 3, etc. And each outcome has some probability of occurring. If those are the only possibilities of my experiment, the sum of the probabilities will equal 1. Those are disjoint outcomes of experiment, right? So what happens if I perform an experiment? Those are all the possibilities. And what I wrote to the left are just the likelihoods of those possibilities. Now, we might have some possibilities being for us exactly the same, giving us the same exact value. You see? So So for example, I mean, you might have an experiment of somebody trying to drive a car, right? Drive a car and actually get to the destination, get to New Jersey, let's say, right? So there are many possibilities. Let's say you drive a car, and if you are not aware, you might get into Bronx, or you might, that's happened to me, for instance, right? Isa navigated me into Bronx, and the roads are very narrow. And it took me more than an hour to get from there. Or I might drive the car and get into Queens. Or maybe I'll drive a car and get, you know, get across the Atlantic Ocean. Those are possibilities, right? Now, let's say what I want is all outcomes, all different roads that get me to New Jersey. There is one road to New Jersey, another road to New Jersey, another road to New Jersey, and other roads that get me elsewhere. So I just labeled, maybe it's a bad example, but you understand. I label the outcomes that get me to New Jersey, the different paths, the different navigation paths that get me to New Jersey out of all possibilities, okay? And them I label by some values, right? And maybe you understand what I'm saying, or I'm completely, you know, today, right? It's just payoffs. You understand? Some situations they give you exactly the same result. So if you're betting in a casino, let's say you have the greens. Every green sector means you win. Every red sector means you lost. You don't care which particular green sector you get, because the payment, let's say, for each green sector is the same. So that's the relabeling, okay? Yes, 1, x1, 2, x2, n, xn. Makes sense? That's the relabeling, and the other thing is the probability. Now, when I apply a function, it's just a relabeling of a relabeling. That means that I just do this. G x1, gx2, gxn. Yes? Good? So that's just another relabeling. So you understand, what am I calculating when I compute expected value? Those are the scores I will actually get. The G's are the scores that I actually get. Do you agree? So we have two methods of carrying that calculation, right? So method 1, and if you want afterwards, I can make it an example, a concrete example, if you want to see the calculation. But method 1 is that I simply look at the individual outcomes, and in my table I just I sum this way. So how many times did so my average, if I play this n times, if I play it lots of times, it's going to be what? It's going to be g of x1 multiplied by probability of 1. In other words, how many times did I get outcome 1, which generated this payment, right? Plus g x2 probability 2 all the way to g xn probability n. That's one way to calculate the average. You understand? Here I focused, I still kept track of which outcomes came about, and in averaging my payments, my payoff per game, what I did is just I saw how many times I got outcome 1, and I just that's how many times I added payment 1. Yes, it is expected value. Okay, so that gives you the expected value of gx. Okay, one way to do it. You follow, guys? I'm not sure if I'm explaining well today, so let me know, please. right? You understand how I am thinking, guys. What is it that you're doing when you calculate expected value? You have to have a very clear and simple way to understand it. What I imagine is that I actually have a list of outcomes per game. You understand? So I see I have tables, and I play billions upon billions of times, and I have a long list of outcomes. So I see how many times I get the outcome, and for that outcome I see how much I get paid, right? So how much I win, right? And so in averaging, I can group by the outcomes. I can take the table and I can sort it by which outcome came about, how many times outcome 1 came about. And then instead of you know, multiplying the outcome, you know, I'm just multiplying the payment for each of them, because each of them produce the same payment. Each outcome 1 produces the same payment, gx1. You agree? Alan, you are skeptical, so you don't agree. Agreed. Okay. You see. Make sure, guys. No, yes, right. Don't be shy. Let me know if anything is not clear, right? So gx1 is how many times I got outcome 1, and I just add up the payments, and then I look at how many times I had outcome 2, and I add the payments, right? And I do that for all of them, and then I divide by total number of games, right? So how many times did I had to add up gx1? It's going to be the number of the ratio of the number of times per total is going to be the probability of outcome 1. Do you see that? Yeah, I will do this. So this abstract way of thinking doesn't cut it for you, I see. All right. I will do an example, sure. Yes? Yes. All right, and then after I say method 2, and then maybe we'll go back to it and you'll see it again, right? Method 2. Method 2 is, so method 1 is group by outcome. And method 2 is group by payoff or payment. You understand? Grouping by payoff is I just sort and I see which values are possible for me, which numbers can I actually get. Instead of, I don't really look how many times I got. Instead of looking at the side that shows me the outcome, I just sort by how much money I get, right? How many times did I get $1? How many times did I get $2? How many times did I get $3 and whatnot? Good. And the result is going to be the same, because all I'm doing, I'm just adding up the same table and dividing by the same number. You understand? I'm just doing it by different orderings. I just group things together. You understand? It doesn't matter if you have a pile of money. I presume you can understand that theoretically, right? I've never seen piles of money, but theoretically I can imagine it, right? So the pile of money, you can add it in any way you like. You agree? You don't have to group 20s together or 100s together. You can add them straight ahead, or you can add them by payoff. Good. So you can do all sorts of sorting. So method 2, group by payoff, and that will be what? So that means the expected value of gx is simply the summation of the possibilities, right? So g of x is y, so it's all y. Probability of so it's y multiplied. So let me say it like this maybe. So it's y such that g of x equal y for some x, and what it is just y multiplied by the probability of getting that y. Good. So that's the other way of doing it. So let me give you a concrete example as Sarah demanded. So let's suppose we play dice, right? So let's say the game is 1, 2, 3, 4, 5, and 6. So this is my sample space. You understand what the probability is of each event. It's 1/6. Good. So let's suppose that what we have is we are going to label 1, 2, and 5. They are going to give you payment of $1. Yes, and 3, 4, and 6. Well, actually, let's make it. Let's not have 6. 3 and 4 will give you a payment of minus $3. You lose money if you get those values. Good. So it's minus $3, and 6 gives you a payment of $6. Okay, that's the game. Okay, now let's suppose that what I have is I have the function squared. Okay, the function is squared. So this is my random variable x. Here you can see it over here. That's my random variable x. And then I want to transition to x squared. What's the transition to x squared? The transition to x squared will be doing what to those values? So the red values they go to 1. The orange values go to 9. Both minus, it's actually, yes, so it's 9. And 6 goes to 36. Yes. Now, how can I calculate what's my expected payoff of x squared? Okay, so there are only 3 values: 1, 9, and 36. Do you agree? So one way to do that, so that would be method 2-way. The definition is method 2. I look at my scores and I see what the probability is of getting them, right? So I see that the possibility is I can get $1 multiplied by the probability of getting $1. That probability is 3/6, correct? You see, because we have 3 outcomes that give you $1, 3/6. Plus another possibility is I get $9, and that's likely to be with probability 2/6. And the other thing is 36, and the probability of that is 1/6. So that's the expected value in that case of my random variable x squared. Do you agree? Now, where did we get the 3/6? Right, look at it. You can still see the 3, 2, and 1. You can still see the probabilities of the outcomes. You agree? So how did I receive this result? It's 1 multiplied by the probability of event 1 plus the probability of event 2 of outcome 2 plus the probability of outcome 5. Do you agree? And then we have 9, and that's the probability of outcome 3 and 4. They're here, plus 36, probability of outcome 6. You agree? And you understand how what I actually added, how I could imagine this result appearing, right? If I play the game many, many times, then in the average, I will see that it's just the score multiplied by the number of times the score is received among my outcomes. And that is going to be the probability, right? The number of times I receive the score 1 among all the outcomes divided by total number of games is going to be the probability. So that's how we receive this result. Okay. So notice how I grouped it. I grouped it by payment. You see payment 1, payment 9, and payment 36. Good. Now I can also group it by outcomes. You understand? So that is just my so by outcomes it would be the following. So method 1, which is not the definitional method, but it's obviously true. Method 1 tells me, well, group it by the initial outcome. So what happens if I get outcome 1, probability of outcome 1 and the payment of outcome 1. The payment of outcome 1 was 1, correct? Plus the payment of outcome 2. You see, payment of outcome 2 is also 1. Next is payment of outcome 3. And what was the payment? And then payment of outcome 4. So what was the payment of outcome 3? I believe it was 9, correct? And then plus payment of outcome 4, it's also 9. Payment of outcome 5 is 1. And payment of outcome 6 is 36. Do you see? Here, here I keep the order 1, 2, 3, 4, 5, 6. Over there, here I grouped by what negative value? There is no negative since I squared it. There are no negative values. There were initially negative values, but now we squared it, right? We are calculating the square. Yes? You're asking why would anybody do that? That's a different story, right? You will see what variables, why you want to calculate expected value of x squared, whatnot. The point is it's just basic arithmetic. It's just grouping the summation either based on the individual experimental outcomes or based on payoffs, and the result should be the same. Do you see that? It's just you sort a table, and before you add things up, you sort the table, and you group it based on which category. Sarah, does it explain what you wanted to see? You see what I'm saying?
Yeah, thanks. It's really intuitive now.
It's extremely intuitive, I hope, right? Yes, of course. The point is, guys, that it's always the same. You understand? It's very intuitive why it always will be the same. Of course, if you have infinite series, if you have infinitely many of them, there is the issue of rearranging sums. Okay, so I'm now going to show you a proof of something, right? So when is that rearrangement going to produce the same results? But in pretty much all aspects where you can imagine applying it, it's very intuitive why that should be working. I hope if you see what I see, then it's trivial. Here is the proposition, guys. If x is a discrete random variable that takes on one of the values xk with probability pxk, then for any real valued function g for which it's absolutely convergent, that's what this means. It's absolute convergence. And if you remember Calc 2, yes, I think I'm missing exactly the Calc 2 guy. Jack is not here. he was bothered with my summation, 2 plus 4 plus whatnot, right? So in Calc 2, if you have absolute convergence, then you can rearrange the terms of the series, and the summation will always be the same. But if it's just merely convergent series, then rearranging the terms might cause the sum to go to a different value altogether. Good. So that's why there is this statement. The statement just tells you that you can rearrange terms without without having any problems. If you're dealing with a finite case, it's obvious that you can rearrange a finite sum. Right? What we did, method 1 and method 2 are just rearranging the summation. Right? It's like if you look at a table, you might imagine if you look at an infinite table, just rearranging terms and adding it up will produce the same results, but mathematically that is not necessarily true. You can create a weird type of bill, a long infinite bill, and if you add the payments one way, you owe a lot of money, and if you add the payments another way, they might owe you money. You understand? It's a pretty funny type of bill. You know what I'm talking about, no? I'll cover this thing and I will tell you what I'm talking about. You are aware of the series, the oscillating harmonic series. Yeah. So it can add up to any number whatsoever. So, in fact, I actually mentioned it right away here, apparently. So rearranging terms, you understand? So imagine that you have the following bill, guys, right? You have, you go to a restaurant or you go to a hotel or who knows what, and here is your bill, right? So maybe what you have to pay $1, but there is a deductible of 1/2 for whichever reason, plus 1/3, and there is a deductible of 1/4, plus 1/5, there is a deductible of 1/6, and so on and so forth, right? So you understand, if you add up this summation this way, you end up, I believe, owing ln of $2. Okay, you have to go and pay them ln $2. You multiply it by 100 or by whatever number if you feel like ln of 2 is not a big, it's chump change for you or something, right? Or minus, I think it's minus ln of 2, I think, but whatever. So you can just figure that summation. I can show you how if you're interested. But if you rearrange the summation, you can go to you can just kind of just move things around, skipping the same numbers. You can go to the court and say those people owe me infinity dollars, right? Or $1 billion or $1 trillion, and they can just go rearrange it and say, oh no, actually the client owes us billions and trillions of dollars. You understand? By rearranging the summation, you can make it add up to pretty much anything you like. Euler found this interesting fact. Isn't it cool? Yes. How you present, and that's, guys, very important also. It's a good lesson. How you present the information, can produce different conclusions altogether. Yes. Yes. So here is the proof, guys. So by definition, the expected value of g of x, if we label it as g of x as y, it's just the sum of the scores that this variable can take times the probability of such scores. You agree? So the expected value of y is just the summation. It's a discrete random variable, which means I can label it as 1, 2, 3, 4, etc. I can index the values. So it's just a summation of y1 times the probability of y1. And how do I get the probability of y1? It's just I sum the probabilities of xk for all the values xk that produce yj. You follow? So in my notes, let's say, how do I, you see, it's just this summation that you see over here. In my notes, you can see it here. You see, that's the summation. by definition, you see? The payment 1, what values produce payment 1? Outcome 1, outcome 2, and outcome 5. And there are some of the probabilities is multiplied here. Good? So this is the summation. And then all I do is I just look at this thing and I can push yj across the sum. And because I pushed across the sum, in the sum, yj can be written as jxk for any k, right? I can just write for any specific k within that sum, they all produce yj. So I can just write it as summation of xk of gxk times pxk. Good? So far clear? No confusion yet? And then what? And then I look at the summation and I just realize that this summation is just a rearrangement of terms, nothing more. Yes? It's just what? Adding it up this way based on the particular values that give yj is just grouping y1 together, then y2 together, then y3 together. It's just rearrangement. Right, so you can just as well just go from k1 to infinity and just put them as g of x1, g of x2, g of x3, etc. And here is another example, just in case you were not satisfied with the previous one. Okay, so suppose that that x can take values plus or minus 1, plus or minus 2, plus or minus n to some n, where the probability of x being, so it can take infinitely many values, you see. So 1, 2, 3, 4, etc., infinitely many values. The probability that x is equal to n is the same as the probability that x equals to minus n, which is 1/2 to the absolute value of n plus 1. You understand what it means? So the probability of 1 is 1/2 squared. So it's 1/4. And the probability of minus 1 is 1/4. Good? The probability of 3 is 1/2 to the power of 4, 16, 1/16. Good? And that's the same as probability of minus 3. So everybody understands? And then I let y be equal absolute value of x. Y is the absolute value of x. So what's the expected value of y by definition? Well, it's just what values can we now take? We can take values 1, 2, 3, 4, 5, 6, 7, right? We can only take positive integer values. So it's the summation as n goes to 1 to infinity of n times the probability of n. And the probability of n is always a sum of the probabilities of getting minus n plus the probability of getting n. You agree? Because we took absolute value. What can produce the same absolute value? The positive and the negative of this number, right? So what produces 1? 1 and minus 1, because we take absolute value. What produces 2? 2 and minus 2. So that's why we only add two things here. Do you understand? Now, if I add, look at it. Here I wrote a k to the minus n, and that's why I kept absolute value here, because it will have to be, taken in absolute value. So what we have in essence is the positive and the negative, they produce the same probability. So it's the same as taking 1/2 to the power of n plus 1, where n is the positive of the numbers, and multiplying it by 2. And that will give us 1/2 to the power of n. And so the summation is n multiplied by 1/2 to the power of n. And if you understood that bullet example, you right away know that the answer is 2. Right, because n times 1/2 to the power of n it's the same as having a pistol or a revolver with only 2 chambers. And then you ask how long will the game last? You see, because n, that's why I tell you watch Deer Hunter, right? That's immediately what I think about. So I look at this summation and I think, oh, I remember I saw that in a movie. Right? That's why I like probabilities. Like I like that type of silly messages. You see something and, oh, I recognize this thing. Some reference that seems kind of coded. Yeah? Good. So this means that this is the number of rounds on average that now this becomes the number of rounds on average that you can play a Russian roulette where there are only 2 chambers for the bullet. And you right away know that that is 2 because you will on average hear a shot once every 2 rounds. Right? And we prove that you can sum it up if you want to. You understand? So on the other hand, guys, what is the other method of calculating the expected value? Right? The other thing is we are not grouping by the payoffs. We don't group by the absolute value. We just group by the actual outcome. So either I get the negative, a negative outcome, a negative number, or I get a positive number, right? And then I take that number in absolute value. So it's this summation where n is a negative number, and I take absolute value of that number multiplied by its probability plus a positive number multiplied by its probability. So when I carry this thing out, I realize with the absolute value, I can convert this infinite series, and it ends up being the same as the one to the right. And so it's 2 times the series to the right, and you multiply it through and you get the same summation. So again, you get 2. That's the same example, but with infinitely many possibilities. Understand? So the only interesting thing about that theorem, why it's interesting, is technically if you are dealing with infinite sums, rearrangements are not always producing the expected result. Otherwise, it's pretty trivial. So, but for this class, it's introduction, and you can almost forget about it. You can almost assume it's always true, but be aware that who knows, maybe you get in trouble. Here is a corollary, guys. And that's one reason, Alan, why such ideas are important, is that if A and B are constants, then the expected value of a linear transformation of X is going to be A expected value of X plus B. Because what can I do, guys? The expected value of AX plus B, I can group it based on the outcomes X, right? So what happens to each outcome X? It's AX plus B multiplied by the probability of getting that outcome, right? And so I can distribute the probability and spread the sum, and I can see that what happens here, it's A times the times X times the probability of X summation plus B times the probability times the sum of the probabilities available for us. Now I know that the first part becomes expected value of X times A, and the probabilities of a random variable always add up to 1, so B is multiplied by 1. Do you follow this calculation, guys? Look at it carefully. Let me know if anything is unexplained and you need something more. Clear? Yes, that brings us now to variance. So knowing the average payoff per game doesn't give us a lot of information on how the game oscillates. Is the game monotonous, or is it, or there are a lot of ups and downs? So for example, imagine that you have the random variable W, which equals to 0 with probability 1. So you always get 0. Or you have the random variable Y, which equals to -1 with probability 1/2 and with 1 with probability 1/2. Or you have the random variable Z, which has -100 and +100, each with probability 1/2. You can obviously see that the expected value for all of them is 0. Yes, but one does not ever deviate from 0. One deviates somewhat because, let's say, you get sometimes $1, sometimes -$1, and the third deviates significantly. You get +100, -100. Right? The expected value is just what you get on average per game, but there is a huge deviation, huge jumps between one game to the next. There is a lot of oscillation here. So we want some ideas on how to measure that oscillation. So for that, we are going to label as mu to be the expected value of X. That's the average, okay? And we can measure how much do we think on average do we expect X to deviate away from mu. So that's what you would have known as standard deviation, and you would have liked to measure the expected value of the absolute value of X minus mu. You understand why, guys? Because this is on average what is the difference between some outcome that you're expecting to see. Good. You understand why absolute value of X minus mu would have been a perfect measurement of the oscillation. Because what you're measuring is how far away on average are the individual outcomes from the average. Right? If on average they're at 0 distance, then you think you're getting the same thing. And if on the average they're at a distance of 100, you expect that you would see numbers that are average plus 100 and average minus 100 type of things. Okay, so it gives you some measure, but this is very difficult to calculate. So usually not convenient to calculate, and instead what you do is you measure that with the square of that number. You use the square distance. Okay, so the square distance will also give you an indication of how much you have, deviation. Okay, so that's how variance is defined. Variance is defined to be the expected value of the random variable minus the average of that random variable squared. Good, and then we have this this observation that's kind of useful for us. You see, absolute value is not a continuous, well, it's not a differentiable function, so it's much nicer to measure the square. So observe the following: the variance of X, I can just expand the parentheses, it's X squared minus 2 mu X plus mu squared. And the probability, the expected value is just this quantity multiplied by px by our, you can see the X squared here, by our previous result. We can either add based on payment, or we can pay off, or we can add based on the particular outcomes of the random variable. Yeah, so we can group it in many ways. We can group it based on initial outcomes, based on the outcomes of X, based on, you see, you can just you have in the table, you have 3 values. You have the individual outcomes, you have the values of X, and you have the values of the function of X. So you can use any of the columns, because what you're doing is you're adding the you just have to find the average of the third column, and you can group using the second column, or using the first column, or using the third column which you're averaging. You understand what I mean? Just to be sure, guys, here is how I think of this. Very simply, I think of this as like this. Here is my sample space outcomes. Here are my X outcomes. Here are my GX outcomes. Okay. So when I calculate the expected value of GX, I am averaging this column. You agree? Now, when I average this column, I can decide how I group it. I can group it by the outcomes of the sample space when I add. I can group them by the outcomes of X when I add, or I can group them by the actual payoffs, or by the outcomes of GX when I add. You understand? It doesn't matter. This is just rearranging, right? How do you present this third column? You can arrange it based on the first column, or second column, or third column. You understand what I mean? Just in dictionary order, right? So if you imagine the sample space outcomes listed in, numerically, first, second, third, fourth, right? You can use that to arrange it. You can use the numbers of X from smallest to largest, so to speak, and list it like that. Or you can use the outcomes in GX from smallest to largest, if you like, or from any other ordering, doesn't matter. Make sense? So that's why you can calculate expected value in various ways. So when I use here, what I'm doing, guys, you see, which just a comprehension check. When I do the summation, which column do I use? You see, this is g of x. G of x is x minus mu squared. Yes. What do I use to arrange my summation? What do I use to average? Do I use sample space column? Do I use x column, or do I use g of x column? Write in the comments. All right. What do I use when I take this average for my sorting? Okay, Roadra says g of x, Nu says g of x. What about the rest of you? Wait for a moment, see if you comprehend. So you see, guys, you don't comprehend them. Well, that's the average. I'm asking how do you calculate it? All right, let's see what we have there. Do we have any messages? No. All right, then we don't understand. Fine, round 3. When you calculate expected value, you're averaging. Do you understand? So anyone here, guys, when I calculate the expected value of gx, I am averaging. Good, agreed. Averaging what? So imagine that we have sample space is simply 1, 2, 3. Okay, and the payments of 1 is 1, of 2 is 0, of 3 it's -1. Okay, that's my x. Good. And then I take x squared plus 1 or something, right? So then I map this into x squared plus 1, and what do I get then? I get outputs that are possible are 2 and 1. Agreed? So 2 and 1 are the outputs. So imagine that this is what I observe. Here I have a triple table. I have outcomes that came out from my experiment. I have evaluation x, and I have evaluation x squared plus 1, which is g of x. Okay, you understand? So in my table, imagine that that I have also I have this thing. So when I calculate expected value of g of x, clearly I'm going to average the third column. You agree? I'm going to average the values of the third column. So suppose you perform the experiment and you see something like this. So outcome 1 occurs here, and that means that payment 1 is occurring here, and over here payment 2 is occurring. Yes. Then again, outcome 1 has occurred here. Then we have payment 1, and the third column gives me 2. Now here I have outcome 3 occurred the next time, and here I have 3 occurred here. So this is -1 and this is 2. Yes. Next, I have outcome 2 occur here, and that is outcome 0, and that's outcome 1. And then again, I have 2 occur here, outcome 0, outcome 1 here. Yes, and maybe one more event. So here we have again outcome 1 occurred here, and that means here we have 1, here we have payment 2. Assuming that this table is a good representation, in other words, imagine that this represents probability perfectly. Okay, so just gives you a complete sense of what's going to happen. So you see, I played how many games? So I played 1 game, 2nd game, 3rd game, 4th game, 5th game. I played 6 games. Assuming, it has to be, this table is imagine it's going forever. Yes, table is going on, but it's going forever. Okay, so then how am I going to average? You see, what's going to be my expected value if this is a good representation? The expected value of g of x is going to be 2 plus 2 plus 2 plus 1 plus 1 plus 2 divided by 6. You agree? If 6 were a huge number, that would be a good representation of the expected value. Are you with me, guys? Right, just imagine the same thing, but it goes to billions and trillions of entries, and then it's really very much like expected value. Good. That's so. No questions. Is that I am taking the average of this column when I calculate expected value of g of x, but I can sort. You see this information? I can sort it. Okay, in 3 ways. Do you agree? Do you see where I have the 3 ways according to the sorting of 1st column in order, or 2nd column in order, or 3rd column in order? So before I add it up, tell me how to sort it using the 1st column, right? Let's sort it using the 1st column. So if you sort it using the 1st column, the results are like this. So 1st column sort. What do you have? You have, here we have x squared plus 1, here we have x, here we have s. 1st column sort means that in my outputs, I look at the labels of s. So I have 1 first, then 2, then 3. Right? So I have 1, 1, 2, 2, and 3. 1, 1, 2, 2, then 3. That's not the order in which the outcomes occurred. I just sorted them by 1st column sort. 3 ones, you're saying. Okay, so thank you. Good. Now, what was 1? 1 produced which value? 1 produced the value 1, and 2 is the value 0. Yes. So then we have the value 1, and that is 2, 2, 2. This is 0 and 0 and 0, and 3 produce -1. Am I right? You see, I just rearranged everything based on 1st column sort. Yes, so 2, 2. Then what we have here is 1, 1, and here we have 2. Make sense? And now the summation is the expected value is calculated as 2 plus 2 plus 2 plus 1 plus 1 plus 2. over 6. Are you understanding what I'm saying? You see what's the difference? There is no difference in this in the calculation, because you're just, well, of course, so we have to know the sample space in X. X by itself as a random variable makes no sense without some underlying sample space, or knowing at least, I mean, maybe I don't know S, right? Maybe I know I forgot about S, and I just know that X occurs, X equals to 1 with some probability, and X equal to 0 with some probability, and X equal to -1 with some probability. That means I deleted S, but there was an S somewhere in the background. I just forgot about it. You understand? I kind of did this experiment so long ago, so many times, that S is now in a black box. But if S is available, and theoretically it's always available, you understand? There is always an underlying space S, I just might not be aware of it. Good? So this is the summation. Do you see the difference? Look at it. 2 plus 2 plus 2 plus 1 plus 1 plus 2. Here it ends up being the same, but you can see that we were adding them in a different order. Now, what happens if I sort according to X? You see, it's 1, 1, 0, 0, and -1. If I do an X sort, so that's second column sort. What do I have? Still same thing. Here is S, here is X, here is X squared plus 1. Yeah, second column sort means that I begin with, let's say, maybe -1. Then I believe there are 2 zeros, correct? And they are 3 1s, correct? Here it is, 3 1s. You see? I did this sort. Now, -1 corresponds to the outcome 3. So this is 3. 0 corresponds to the outcome 2, I believe. The outcome 2. The outcome is 1, 1, and 1. You see? And then what about X squared plus 1? X squared plus 1 is simply going to be 2, 1, 1, 2, 2, 2. You see that the summation is now different. In different order. Summation is going to be the same, ratio is going to be the same, but sorting is different. Make sense now? Now, if you understand what I'm talking about, you just tell me, please. In this situation, you see, when I calculate variance and I use this formula, what sort of sort am I producing? I'm sorting based on which of the columns? You see, in theory, we have 3 of them. There is a column representing the sample space. There is a column representing the random variable X. And there is the third column representing the random variable G of X. Where in this case, G of X is X minus mu squared. So when I have this formula here, this means I calculate the expected value of that random variable based on which sort. I sorted it by the sample space, by X, or by G of X, by the possible values of G of X. No? What is this, guys? So what is this? This is G of minus 1, right? This is G of 1. This is G of 1, G of 2. sorry, g of 0, g of 2, g of 1, sorry. Yeah. What sort is happening here? Yes. Yes. X. Don't you see why X? Because this is G of the particular value. Just to the 0, 1, 2, it's here it is. And that's the probability of X. So that's the second column sort. Don't, you see guys, try to understand it, because if you do, you will play with expected value. It's going to be magical. We're going to see some very interesting results relating to expected value. And all of those results are trivial if you realize, I'll show you some examples later, right? If you realize what is expected value, and you realize that you can solve it, at least theoretically, by sorting it 3 different ways. Yes? The expected value of a function, I mean, right? So here, back to this problem. So the expected value of x minus mu squared, you see, how do I know that? Here I'm not grouping by the possible values that x minus mu squared is equal to. I'm grouping based on the possible values that x can take. You see, if x takes this value, then the function takes this value. So it's x squared minus 2 mu x plus mu squared times the probability. I can then distribute the probability. This is what? This is the expected value of x squared. You recognize it here. Yes, Alan, you see, x squared times px. Here, it's the expected value of x. And here, it's just mu squared times the sum of the probabilities. And the sum of the probabilities of x must add up to 1. So that means that's the expected value of x squared minus 2 mu expected value of x plus mu squared. But this expected value of x is another mu. So we have expected value of x squared minus 2 mu squared plus mu squared. And that means that the variance is equal to the expected value of x squared minus the expected value squared. This, by the way, right away tells you, because look at it, this number is positive. It right away tells you that the expected value of x squared is always bigger or equal to the square of the expected value. Yeah? That's not obvious when you look at this line, but it's obvious when you look at that line, because here you're only adding up positive numbers multiplied by fractions, by positive numbers, right? The sum is positive. Yes? And if the sum is positive, that means that this difference is bigger than or equal to 0. So let's calculate one or two things. So let x be the outcome of tossing a die. Calculate the variance. Okay, can you calculate the variance? Let's hide it. You understand the problem, guys. The outcome of tossing a die, a fair die. So you know everything about what happens here, right? What's the expected value? Okay, Flo, thank you. All right, thank you, Nora. Yeah, well, I'll hope in a moment. Or to be honest, I will not help in a moment. It's a cliffhanger. Come back next time, right? If you are interested, I'm not sure it's a good thing to show you, but yesterday I watched a training for German forklifters, and that killed me. I was choking from laughter. Would you like to see that? If so, it's 9 minutes. Stay with me, and if not, goodbye. 333. What's that? All right, so I'm stopping the recording.